Lesson 2, Populations. Questions to help us unlock the big question that we will answer today are: how do populations change in size? And what factors limit population growth? My Planet Diary. Prairie dog picker-upper. Did you know that vacuum cleaners do more than just clean carpets? Across the Great Plains, farmers are using specially designed vacuum cleaners to help them remove black-tailed prairie dogs from the farmland. Prairie dogs can eat crops, cause soil erosion, and endanger cattle and farm machinery. The prairie dog vacuum uses a 4-inch plastic hose to suck prairie dogs out of the ground at 483 kilometers per hour. The prairie dogs end up in a padded tank, usually unharmed. They are then relocated or donated to the United States Fish and Wildlife Service to be fed to endangered eagles, hawks, and black-footed ferrets. Question 1 says, if all the prairie dogs were removed, how do you think the prairie ecosystem would be affected? Sometimes when organisms are removed from an ecosystem, that affects other organisms. So the organisms that depend on the prairie dogs for food could starve, and what the prairie dogs eat could continue to grow and just cause mass chaos by having an abundance or too much of it there. Number 2 says, should prairie dogs be used as food for endangered species? This is an opinion question, but I'd say that maybe one type of organism is not more important than another type of organism. Or I could say, well, I think the bald eagles are dying out, so it's not fair that those animals should die out when we have a lot of prairie dogs. What do you think? How do populations change in size? Ecologists are scientists who study biotic and abiotic factors of an ecosystem and the interactions between them, remembering that biotic factors are living or were once living, and abiotic factors are not living and have never in their non-lives ever lived. Some ecologists study populations and monitor the sizes of populations over time. Populations can change in size when new members join the population or when members leave the population. Births and deaths. The most common way in which new individuals join a population is by being born into it. If more individuals are born into a population than die in any period of time, a population can grow. So in the birth rate, the number of births per 1,000 individuals for a given time period is greater than its death rate, the number of deaths per 1,000 individuals for a given time period, the population may increase. The main way that individuals leave a population is by dying. If the birth rate is the same as the death rate, then the population may stay the same. In situations where the death rate is higher than the birth rate, then the population may decrease. To the math. Depending on the size and age of the female, an American alligator can lay between 10 and 50 eggs per year. Number 1 says to graph. Using the data table and colored pencils, create a double bar graph showing alligator births and deaths for 4 years. They then want us to label the X and Y axes, write a title for the graph, and fill the graph using colors shown. So we have blue and we have red. So let me find my blue. For year 1, we're going to start where it says 1. The births were 32. So that would be year 1, go up to about 30 and a little bit above. Here we go. This is births for year 1. Deaths for year 1 were 8. So I find year 1, 10, and it's just below it. We do the same for year 2. Year 2 was 28 births, so it's just below 30. And deaths were 13. So it's almost halfway between 10 and 20. We do the same for year 3. Year 3 we had 47 birds. That's a lot of birds. We color it in. And of course we're pretending that Miss Reams is drawing these boxes in perfectly, because obviously they should be. Year 3 deaths were 21. In year 4 we went down a little bit with our birds. It's now 33. So almost halfway. And then 16 deaths. Boom! They also want us to label the x-axis and the y-axis. So down here, what are these numbers telling us? Well, that's how many years it is. So the first year, second year, third year. On this side, the numbers here, they're telling us the number, birth, and death. So the number of births and deaths. So we did that, we did that. We now want a title for our graph. We don't have to be creative. Why is it? This looks funky. Let's try different. Alligator. What's 2 L's? Birds. And deaths. Doesn't it be fancy? Boom. Fill in the graph using colors. Boom. Did it. Number 5 says, develop hypotheses. What factors might explain the number of births and deaths in year 3? What do you think? Well, maybe we had more food. Maybe a lot of food was in year 3 they didn't have before. Maybe there was more construction that could have tampered with the habitat of these alligators, because we can see that this is the most births and the most deaths. So maybe those 2 things happen, but there are many other things that could have happened to affect these numbers. The population statement. When the birth rate in a population is greater than the death rate, the population will generally increase. This can be written as a mathematical statement using the is greater than sign. So if birth rate is greater than death rate, population increases. However, if the death rate in a population is greater than the birth rate, the population size will generally decrease. This can be written as a mathematical statement. If death rate is greater than birth rate, population size decreases. Immigration and emigration. The size of a population can change when individuals move into or out of the population. Immigration means moving into a population. Emigration means leaving a population. For instance, if food is scarce, some members of an antelope herd may wander off in search of better grassland. If they become permanently separated from the original herd, they will no longer be part of that population. Figure 1 says, in 1898, white-tailed deer were almost extinct in Iowa due to overhunting. The deer population was re-established as animals from Minnesota, Wisconsin, and Missouri immigrated into Iowa. Remembering, immigration reminds Miss Reams of in, so immigration means you're going into a new place. And emigration, you're leaving. So using your classroom or at home, because that's where you are, describe an example of immigration and emigration. One example for immigration could be a new student, Sally, was added to my English class. She had moved from Denver when her dad was transferred from work. So Sally moved into a new classroom. She immigrated. For emigration, we could have Jordan had his schedule changed the first week of school and was moved into a different science class. That means Jordan left our science class. He emigrated from our science class. But he also went into a science class. So he emigrated from ours and immigrated into another one. Graphing changes in a population. Changes in a population's size can be displayed on a line graph. Figure 2 shows a graph of the changes in a rabbit population. The vertical axis identifies the number of rabbits in the population, while the horizontal axis shows time. The graph represents the size of the rabbit population over a 10-year period. So figure 2 says, the graph shows how the size of a rabbit population changed over 10 years. We know just by looking at the graph, from 0 to year 4, more rabbits joined the population than left it, so the population increased. But from year 4 to 8, more rabbits left the population, so the population decreased. Number 1 says, interpret data. In year what, the rabbit population reached its highest point? Well, if we look at our graph and we go year by year, and we go up to our highest point, that tells us year 4 is when the rabbit population reached the highest point. Number 2 says, what was the size of the rabbit population in that year? Well, if we go to year 4 and we go up to our dot and we go over to our number of rabbits, we know it's somewhere between 800 and 900. But it's in thousands. So we can say about 850,000. Number 3 asks, how do you think the rabbit population affected the fox population over the same 10-year period? There are many different answers to this. One could be that the fox population changed in relation to its food, presuming that the foxes in this population are eating rabbits. As the number of rabbits increased, the number of foxes could have increased. But the number of rabbits decreased, then the foxes would also decrease, either by dying out or by having to go in search of food elsewhere. Population density. Sometimes, an ecologist needs to know more than just the total size of a population. In many situations, it is helpful to know the population density, or the number of individuals in an area of a specific size. Population density can be written as an equation. Population density equals the number of individuals divided by the unit area. For example, Suppose you counted 20 butterflies in a garden measuring 10 square meters. The population density would be 20 butterflies per 10 square meters, or 2 butterflies per square meter. Apply it. In the pond on the top, there are 10 flamingos and 8 square meters. The population density is 1.25 flamingos per square meters. What they did, we know that, there we go. We know that population density, I'm going to use PD, equals the number of individuals over unit area. Change the size of my pen. So what they did is they counted each one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And they knew population density equals 10 divided by the unit area, 4 meters times 2 meters. So that's 4 times 2, 8 meters squared. And if you divide that, you get 1.25 meters squared. So number 1 says, what is the population density of the flamingos on the bottom pond? So we need population density equals, well, how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There are 20. So we have 20 flamingos divided by the square meters, 4 times 2, 8 meters squared. And by the power of calculator, that means we get about 2.5 flamingos per, that's what that dash line means, meters squared. Number 2 says, if 14 more flamingos landed in the pond on the bottom, what would the population density be then? Okay, so looking for population density, but now we're adding 14. So 0 plus 4 is 4, 2 plus 1 is 3. So now let's say we added more birds, woo, and now we have 34 flamingos divided by, well, our area hasn't changed, it's still 4 times 2, so it's still 8 meters squared. And if we do 34 divided by 8, now we get 4.25 flamingos per meters squared. Number 3 is a challenge question. What do you think would happen if the population density of flamingos in the pond on the bottom became too great? Well, if we kept adding flamingos, look at this, we keep adding birds, sooner or later what's going to happen? We're going to run out of room. No room. So one, it's going to be super crowded. They're going to be like bumping arms with each other and probably getting sick because this is following the guidelines. Stay home. This is not 6 feet away. So there's no room. They're going to get sick. They're probably going to eat all the food. So there's not going to be any food. So eventually, probably, the flamingos are going to start dying out. That would be sad. Sad day for flamingos. What factors limit population growth? When the living conditions in an area are good, a population will generally grow. But eventually, some environmental factor will cause the population to stop growing. A limiting factor is an environmental factor that causes a population to stop growing or decrease in size. Some limiting factors for populations are weather conditions, space, food, and water. Climate. Changes in climate conditions, such as temperature and the amount of rainfall, can limit population growth. A cold spring season can kill the young of many species of organisms, including birds and mammals. Unusual events, like floods, hurricanes, and the tornado shown in Figure 3, can also have long-lasting effects on population size. Figure 3 says, a tornado or flood can destroy nests and burrows. Name 2 types of natural disasters you think can also limit population growth. Well, we could have, can I write? Earthquakes, volcanic eruptions, droughts, where floods we're getting too much water and droughts we're not getting any water. Our cause and effect on the side over here. As you read about the 4 factors that can limit populations, fill in the graphic organizer below. So we have our effect, well, that's going to be limits growth, but what causes growth to be limiting? Well, we know climate. We also know, so that's our weather conditions, so climate. Space, food, and water. So space, food, and water. Space. Space is another limiting factor for populations. Gannets are seabirds that are usually seen flying over the ocean. They come to land only to nest on rocky shores, but the nesting shores get very crowded. If a pair does not find room to nest, they will not be able to add any offspring to the gannet population. So nesting space on the shore is a limiting factor for gannets. If there were more nesting space, more gannets would be able to nest. The population could increase. Figure 4 shows how space is also a limiting factor for plants. The amount of space in which a plant grows determines whether the plant can obtain the sunlight, water, and soil nutrients it needs. For example, many pine seedlings sprout each year in forests, but as the seedlings grow, the roots of those that are too close together run out of space. Branches from other trees may block the sunlight the seedling needs. Some of the seedlings then die, limiting the size of the pine population. Food and water. Organisms require food and water to survive. When food and water are in limited supply, they can be limiting factors. Suppose a giraffe must eat 10 kilograms of leaves each day to survive. Oh my god, that's a lot of leaves. The trees in an area can provide 100 kilograms of leaves a day while remaining healthy. 5 giraffes could live easily in this area because they would just need 50 kilograms of food a day. But 15 giraffes could not all survive. There would not be enough food. No matter how much shelter, water, and other resources there were, the population would not grow much larger than 10 giraffes. The largest population that an area can support is called its carrying capacity. The carrying capacity of this giraffe habitat would be 10 giraffes. The size of a population can vary, but usually stays near its carrying capacity because of the limiting factors in its habitat. Figure 4, we have a tulip field, possibly in Holland. If no more tulip plants can grow in this field, the field has reached its carrying capacity for tulips. Name 3 things a plant needs to survive. I'm going to go with a plant probably needs sunlight, water, and minerals. That is it for lesson 2. The next lesson is going to be interactions among living things. We figured out what living things are, what they need, and now we need to find out how they interact with each other. Make sure you finish the worksheet that goes along with this, and I will talk to you soon.